You declare a configuration object, assign it with the const keyword, and pass it to a utility function. A few lines later, your application breaks. The user ID inside that object has inexplicably changed. The assumption is usually that const makes the data itself immutable. It does not. The const keyword only prevents the variable identifier from being reassigned to a completely new value. It offers zero protection to the properties inside the object. To see why this happens, look at the engine's memory architecture. The call stack holds the variable identifier, but the actual object data lives in the memory heap. Assigning an object only stores the memory address pointing to that location. Variables do not actually hold objects, they hold pointers. When you pass that const object into a function, you are passing the pointer. Multiple parts of your application now share the exact same reference, creating the conditions for an unintended state leak. Managing these memory references manually becomes a primary defense against unpredictable state mutations in complex applications. Securing your data requires 3 steps: manipulating hidden property descriptors, strictly enforcing extensibility rules, and managing the algorithmic cost of cloning data when references must be severed. Navigating these 3 hidden layers provides the specific controls needed to prevent reference-based bugs in production environments. Every key-value pair you write is governed by a hidden metadata object known as a property descriptor. The engine automatically generates this descriptor, flipping 3 Boolean switches to true: writable, enumerable, and configurable. Toggling enumerable to false hides the property from iteration. Toggling writable to false locks the value, throwing a type error on assignment. These are data properties, which hold actual values. Accessor properties operate differently, utilizing internal get and set functions to compute values on the fly. Strict engine rule: a property descriptor cannot possess value or writable attributes if a getter or setter is defined. Attempting to mix them will throw an error. Every JavaScript object functions as a configurable logic container, deeply governed by these internal permission flags at the engine level. Manually configuring descriptors for every single property is inefficient. To lock down state at scale, the engine provides object-level batch operations. Object.preventExtensions applies a structural barrier, actively blocking new properties. Object.seal escalates this, preventing deletions and setting properties to non-configurable. The absolute lockdown is Object.freeze, which fully seals and flips all data to read-only. But there is a critical architectural vulnerability here. Object.freeze is a purely shallow operation. If the frozen object contains a nested object or an array, the engine treats that nested data as a completely separate memory reference. The top-level pointer is locked, but the nested object remains entirely mutable. Because JavaScript immutability is shallow by default, achieving absolute data lockdown requires recursively traversing the object and freezing the entire chain of references. Since recursively freezing nested data carries a heavy performance cost, the standard alternative is to safely clone the data, severing the shared reference entirely. A shallow copy, achieved using the spread operator or Object.assign, only duplicates the top-level primitives. The new object gets its own container, but any nested arrays or objects are still pointing to the exact same shared memory address. This chart shows the hidden algorithmic cost of the spread operator. Every time you spread an object inside a loop, you force the engine to reallocate memory for all existing properties. What starts as a linear operation rapidly compounds into an O(n)² curve as the dataset scales. To completely sever all shared references, you need a deep copy, the recursive duplication of the entire node tree. For years, the standard deep copy workaround was passing data through JSON.stringify and parsing it back into objects. This method causes severe data loss. JSON serialization destroys dates, maps, sets, and crashes completely on cyclic references. The modern enterprise solution is the structuredClone API. This built-in function leverages the HTML structuredClone algorithm, perfectly duplicating complex object types like maps and dates, and can safely traverse and replicate cyclic references without throwing an error. The architectural rule is to match the cloning tool to the structural depth. Use the spread operator for flat state and structuredClone for deep state. Managing data integrity requires a complete mental model, controlling metadata at the descriptor level, protecting object boundaries via freezing, and duplicating trees safely via cloning. The JavaScript heap is highly interconnected. You must assume every object is a vulnerable, shared reference until it is explicitly locked or cloned. These raw memory mechanics dictate the performance of modern UI frameworks like React and Vue. Those systems calculate when to re-render the screen by checking referential equality. They compare memory pointers, not the data inside the objects, relying entirely on strict immutability rules to trigger UI updates efficiently. Mastering JavaScript object internals provides the bridge between being a framework user and a software architect.